Hi class, welcome back. So this is a continuation of 7.1. So these are the two of the practice problems that we had there. They're actually very distinct as what we've done before. Sort of, they have a same concept, but there is a little twist that allows us to extend our concept of understanding for this area between the two curves. So in practice 4, it's asking us to find the area of the region between the graphs of the function f and g. Now, what if we are able to draw the picture? We can clearly see that these two actually, and one thing that we emphasized last time was that when we're doing the area of the curve, it's important for us to recognize what is the top function and what is the bottom function. But there's a problem in this problem because if you notice, f is the top function for this one right here. F is the biggest one, is the top one, and then but over here in the second part, the function the f of x becomes the smaller one. So there is a change of position, right, between the two functions, and so that creates a problem because so far the only formula that we knew was something of this form, right, where you have the top function minus the bottom function, right? And I emphasized last time that that's sort of a big deal, right, in order for us to find the proper area on the curve. Otherwise, we end up getting, if we do it backwards, then we end up getting it sort of the negative value, and obviously that would be wrong. So, but what we're gonna do here is it's sort of by just using some basic logic is, well, if we can distinguish where these two functions change positions, then we can separate finding the area between the region to two parts, right? We'll find this first, and then we'll find this one first, and then we'll find this one second, right? So we just separated two different problems, and then there you go, right? We're done. But obviously we will need to figure out where these two changes happen, and just like before, we can do that by simply knowing where the two functions equal each other. And it happens to be that these two functions equal each other between three points. Now, you might be asking yourself, okay, why is this if it says there to find the area on the region between the graphs? You might be thinking, wait, hold on, because it seems like this region on the right side is still between the graphs. And this region over here is also between the graphs, and you're correct, right, in that sense. But it doesn't really make sense for us to look for that, right? It doesn't make sense to find the area between over here and the area in here. It doesn't really make sense if you think about it just for a second. How big is the area on the right side? Don't you think that it's just going to be infinite? So that's going to be infinite, right here on the right side. So that's infinite. And also over here is going to be infinite, right? Because there's infinite space. So it doesn't really make sense in the context of the problem. Why would we bother finding then the area, right? So it doesn't really make sense. So I hope that kind of gives you an idea that, oh, okay, we're just finding the area in here, between here and there, because we know the area is going to be finite, right? So I hope that kind of gives you an idea why we are sticking between those two positions. So anyways, so we're going to set both the f function and the g function equal to each other, and then solve for x by simply adding x squared and then subtracting 2x. And that gives us this right here. Then we can start by factoring x, right? Factor x because both of them have it, and also factor the 3 because that's also a common factor. That will give us 3x times x squared minus 4 equals to 0. We know that this is the difference of squares, so we can factor it out as x minus 2, x plus 2. So once we factor it out equal to 0, right, we can use the zero factor property to find these three values, right? And there you go. So we found the three values, and so that means that we have these three functions. Now, obviously, by having three values without looking at the picture, right? By looking at the picture, we will know, okay, we're sort of having, if I separate this to -2, 0, and 2, we can kind of figure, oh, we have two regions. Now if we don't know the picture, we won't know which one is the top function and what is the bottom function. But you can simply just do that, right? And I'll do that. I'll do this real quick here. If I make my line -2, 0, and 2, and I know at x equals -2, 0, and x equals 2, I know there is a intersection, right? Intersection. Or maybe I'll say like they're both equal each other. F and G are equal to each other, right? But then what we are interested in is to know what happens in between, right? Whether F is bigger or G is bigger, right? So what are we gonna do? Just practice. Just try a number, right? Plugging -1, right, into F. Plugging -1 into F here. Plugging -1, -1. What would that give us, right? I think we can do this in our head, right? This is +10, -1, -3. So -4 plus 10, it will give us +6, right? So I'm getting a 6 from here. And then what about over here? What do we get from -1? We get -1. We end up getting let's see, -1 will give us -1 there, and this -2. This will give us about -3, right? Somewhere around -3. So obviously we have here that F is bigger than G, right? And then you'll do the same thing with x equals 1. And then in this case, I believe we will get here -10, -1, +3. So that would be was it +10, -1, am I getting this just double checking here real quick in my head. Oh no, never mind. This is negative. No, sorry. This will give us -10. Sorry. This will give us -1, and this will give us 3. So it'll give us -8, right? -8. So that'll give us -8, and then we plug in here. You see how we did this without even graphing? So we found these 2 points without graphing, and then once you find the 2 points, then you can determine who is top and bottom by just plugging a number in between those two, right? And that's it, right? Once you make the conclusion, right, it's sort of nice if we can summarize it. And so we're gonna say from -2, 0, F is greater than G. From 0 to 2, G is greater than F. So that's all we need to know, right? Because now we can go ahead and set up the problem, right? A to B, right? From A to B, top minus bottom. Plus from A to B, right? This is A, this is B for the second part, from top minus bottom, right? So top minus bottom, right? Top minus bottom, right? It's very important that we're doing subtraction. We already know why subtraction. And then once we replace F here, we'll do it with parentheses, followed by the minus, replace G here, follow with parentheses. Parentheses are very important. If you don't put the parentheses, then you're not going to get the correct answer because you will forget to distribute the negative. Same thing over here. We have G is this, and then minus is minus, and then F is this, right? We'll put it in parentheses. We'll use the distribution. Yes, we'll have to simplify each one, and that's what we got here. And then integrate using power rule, basic power rule, which we know how to do. And then we'll plug in the zeros and then plug in the negative 2's, right? Again, don't forget the parentheses when you put in the zeros, then minus when you plug in the negative 2. And plus, right, this is plus, you're adding both regions. And then the second part, when you plug in 2, when you minus when you plug in 0. Okay. And then you add them together, and that gives us negative 24. So we get negative 24 from those two, and then positive 48 from those two, right? And then we got 24. Anyway, so we got the result, right? But you guys see how the concept is, right? It's sort of kind of really cool how we were able to find the area between two curves, right? And then this is just an extension that we can do this we can actually do this for anything. I mean, we have this many, right? You can do it as many regions as we need, right? We can just extend this concept as many regions as we need, right? So this sort of kind of gives us this step to infinite possibilities, right? All right. So that's a great example, sort of consistent with what we discussed before. Is just sort of like an extension, but practice 5 is sort of kind of cool. It's very different though. This one is different, but it sort of makes sense, right? In the long concept. So in this example, we want to talk about two things. First, why we cannot do it the normal way. And then that will give us the answer to sort of look for an alternative. Now the alternative is not so different than the original. We just gotta see in a different perspective. All right, so let's begin. So let's just talk about the problem, right? Find the area of the region bounded by the graphs, right? And if you guys notice, these are indefinite, right? They're not solved for y. They're solved for x, right? That sort of kind of like will give us a hint in the future that we should be doing it the alternative way. All right. So, anyways, if you graph this, you can graph it by solving for y, and you will see that this is a parabola. But even then, if you guys see it, this sort of gives you a parabola. This looks like a parabola in respect to y, right? So it's a parabola because it's a negative, it's facing down. Right, so it'll be a parabola facing down, but because you have a 3, then it's shifted 3 up, right? So we can use the same concept that we would have done for the normal setup of when x is the independent variable of y. So it's very similar, right? And then here, this is a linear. If you pretend that this is a linear, this is the line, right? But if it's being shifted, then it's going to be shifted this way. So it's going to be this line right there. Anyway, so this is the graph. If we're looking for the graph of this, we're going to encounter a problem, because remember that in order for us to find the area of the curve, we need to know what's the top function and what's the bottom function, right? We need to know that. Needs to be explicitly known, right? Well, from here to here, right, that's not a problem, because we know that the line happens to be the top, and we know that the parabola happens to be the bottom. But the problem happens after this, from here to there. If you notice, from here to there, from x equals 2 to x equals 3, the same function happens to be the top and its bottom. So that's actually very, very hard for us to actually work with. There's an alternative way we can do that, but the concept, it's not as sophisticated as the one we're going to discuss. So that therefore we cannot do it this way, right? We cannot do this and then just say, oh, we're going to find the area of this region because this is the problem. I'll explain it again, right? Again, the reason is because we need to know exactly what is the top and what is the bottom. And that's not a problem from here to here, because it's clearly that this is the top and this is the bottom, right? But after you move on from x equals 2, then the problem begins, because here the top function happens to be the same function as the bottom function. So it is sort of a problem. Anyway, so the alternative way is for us to see it in a different perspective. If you guys can kind of, I'll do this. Maybe I think it's gonna work. If you guys think about it this way, let me see if I can. And see, I think I can do a resize. And so what I'm going to do is I want you guys to see it this way. So think about that you're able to see it this way. Do you see what I'm saying? See it with a different eye. See it with x being the x function and the top function, and then y, so sorry, x being the dependent variable and y being the independent variable. So now if you see it this way, won't you be able to say that, hey, if we try to do the same concept where we have top function, I'm going to use a different color. If we use a different, if we use a top function, the top function would be this function right here, right? And the bottom function would be this one right here. And we can do that from positive 1 to negative 2, right? So there's no more that problem where we are having to deal with the top part being the same as the bottom part, right? So I hope that kind of makes sense. So we can see it that way. Now, unfortunately, right, when you don't have the ability to do what I just did with my notebook here. So instead of what we're gonna do is we're gonna have to get used to it, be able to see it the way we had it before. So like this, right? But the concept makes sense, right? We're gonna focus this way now. We're gonna do it, the height of the rectangle will be focused horizontally. That's why this is known as the horizontal approach of the curve, right? And so what we're gonna do is we're gonna do the top function. The top function will be this, right? Which happens to be the parabola. Which one looks like a parabola? This one. And then we have over the bottom part will be the linear. Which one is the linear? This one. So you see, it's very consistent with what we had before, with the caveat that in this case we will solve for x. We will solve for x and deal with y as the variable. So there you go, right? So we have that the top function will be f and the bottom function will be g. And then now you have to figure out what are going to be the endpoints, right? What are going to be the endpoints? So we're going to actually go from negative 2 to 1. How do we know that? You can set them equal to each other and solve for y. So you see how the boundaries have to be y now? In the other approach, in the original approach, where the boundaries were x, here the boundaries are in terms of y. So everything is sort of like backwards now, right? Your x is y, your y is x, right? So sort of think about it that way, and the concept works so super nice, right? So once you figure that out, right, then you just work the same way, right? Top function minus the bottom function from a to b, and the same thing happens, right? Now you're dealing with dy, right? Just make sure that you note that, right? The dy happens to be your delta y. Right, this width happens to be the difference of y, because y is measured up and down. All right, so everything else is the same, right? We're going to deal with simplifying these two. We have to distribute those two, and we will simplify it using basic algebra. So then we'll do the integration by using power rule. We're going to evaluate integrate from 1 to negative 2, and then we'll plug in first the 1, and then plug in the negative 2. You can sort of simplify this to be negative 1/3, negative 1/2, and then positive 2. This becomes negative 8 with a negative in front of it becomes positive 8, positive 8/3. That's positive 4 over 2 with a negative becomes negative 4 over 2 plus negative 4, right? And then you can distribute the negative and then start combining like terms. So that would be this part. This minus this will give us this, and then 2 minus negative 4 will give us this. And then you'll simplify that, gives you negative 9 over 3, 3 over 2, plus 6. Combine, this simplifies to be -3. Combine those two, that gives you 3. Add them together by having common denominator, and that gives us 9/2. So this area is 9 square units, right? The area doesn't depend on the structure. It only depends on the structure of the graphs, right? The region. So it doesn't really matter that the fact that we're dealing with doing a different perspective. So, excuse me. So I hope that this kind of makes sense. It's actually a very nice technique that I want you guys to really think about it, and I want you guys to be able to master as well. And it's not very different. It's just different eyes, right? Different perspective. So I hope you guys find this helpful. Please let me know if you have any questions. See you guys next time.